Good morning, everyone. My name is Shuning. I'm from Uber. I'm an engineering manager at Uber's machine learning platform, also known as Michelangelo. You might have heard about it. Together with me, Di Yu and Michael Mui. These are all engineers in the machine learning platform team at Uber. At Uber, we have been using Ray to power some of the machine learning workload for quite a while. We are collaborating with Anyscale. Today, I want to take this opportunity to share with all of you our journey in using Ray and some of the interesting stuff we developed. And our topic is large-scale deep learning training and tuning with Ray. Just a quick introduction for ourselves. I've been at Uber for more than 7 years, and for the past 4 years, I have been on a journey to bring deep learning as a capability to Uber's machine learning platform. Dee here specializes in the Ray-based deep learning infrastructure, and Michael has a lot of experience in building distributed training infrastructure, hyperparameter optimization, and model representation evaluation. So in today's talk, it's only be 30 minutes, but it's packed with content. First, I'll be giving a brief talk about the journey we have over the multiple years developing machine learning platform at Uber. As you know, Michelangelo is one of the early pioneer concept developer of this machine learning as a platform. After that, Dee will come in and talk about large-scale deep learning powered by Ray. And then Michael will talk about evolving this hyperparameter search, which we initially have at one platform, and then we migrate into Ray using RayTune. Finally, I will give a closing remark and also point you guys to some of the resources, online resources, and blog posts that we have written in the past in order for you to deep dive. So first, let me just give an overview of Michelangelo. Michelangelo is an end-to-end machine learning platform that basically integrates well with Uber's data infrastructure to help our machine learning engineers develop and productionize their models quickly. At Uber, all our data is stored in the data store. In this slide is the basis feature store. But we also take a lot of streaming data, and we do processing, and those become batch feature store or in real-time feature store. Why do we do that? This is because for any model, we have contextual data, like data that only is related to the model itself. But across different models, we all have a lot of shared data pipelines, shared features that's used across many of these models. That's why we build this online, offline, consistent data store. In the middle, there's the model training module, which is a generic module that executes the training. We support traditional machine learning models such as linear or logistic regression to the boosted trees, and then, of course, the deep learning models. After the model is trained, I store in our local internal model store where we manage like the checkpoint, we manage the lifecycle of these models, and give our users an operational panel to deploy. We have two ways to deploy the models. One is the RPC. This is very similar to what you have seen in today's demo by Robert. We also have the batch prediction jobs, where we can kick off a batch, like large-scale prediction job on the data table on the Hive, and then write the output back to the data lake in a different table. As I said, Michelangelo has been in a multiple-year journey. It started in 2016. That's our first generation. Our first generation is basically a pure Spark-based application, more like a monolithic Spark-based application. And we only support the algorithm that comes with it in a Spark MLlib. And then in 2018, we start to have an increasingly larger demand on deep learning. Now, with the existing Spark system, what we did was bolt on the deep learning capabilities on top of Spark. And then since 2021, we have been in this new journey of taking Ray and using Ray as the unified compute framework to power both machine learning and deep learning workload here at Uber. In the next couple of minutes, I will just talk about this in much more detail. So this is our first generation machine learning platform. This is basically one big Spark application. On the left-hand side, we basically do a Spark SQL join between our batch basis table, which is the model-specific feature, and then also the batch feature store, which is the common features across different models. And then this join table get passed through a first pipeline of a series of transformers, such as standard scaling, such as one-hot encoding or string indexers. So these are very, very standard Spark operations. After that, the data frame is passed through the second pipeline, which is the model fitting, post-train, transform, and evaluation. Right. So all of these are very straightforward Spark application style. The resulted artifact here is in the yellow box, which is a Spark servable Spark pipeline that contains multiple transformers, like feature transformers and scoring models. And then this servable model is going to be used in both real-time serving and the batch serving. Now, in order for us to have a high-performance real-time prediction service, we actually make our own customization to Spark Spark pipeline, and we open source that as one of the Spark ticket. It's like right now it's in a patch format, patch status. But the idea is that we don't need a Spark context to use these transformers. We just we can expose the right interface and use the internal algorithms. Since 2018, like I said, Uber's basically a model, which is in classical machine learning models, are getting saturated. And then we basically, all the teams are starting to look at deep learning. Now, deep learning presents a lot of new challenges on this existing Spark system. Notably, we were using Spark 1. I think remember it's at 2.x, and we have a GPU executor problem. So basically, like we have some work that needs to be done in CPU, some work needs to be done in GPU, and then the Spark data frame is also not very conducive to this mini batch shuffle that is very typical use in deep learning training. And then we need to also reduce, basically, a distributed GPU training. At Uber, we developed a open source software called Horvath, and I'm sure many of you might have heard of it. It's an open source library for distributed deep learning. So now, the best way to execute a Horvath job is actually a standalone distributed container job that we launch to a cluster. Now, how do we marry that with the Spark pipeline? Well, what we did was also open source. It's called Horvath Spark estimators. So essentially, this is a Spark estimator syntax, but that can be launched and executed within Spark. But then, it will do the Horvath thing. So let me just illustrate to you in this slide. In this world, what happened is basically we have the first Spark application that's the feature preparation and transform. And then we will call the Horvath estimator's fit function. The fit function is going to write the data into HDFS and then kick off the distributed GPU job. The GPU job will run on its own. We'll stream the data from the HDFS and then do the training. All right, and the resulted model is be wrapped in a custom Spark transformer and sent back to a Spark context so we can construct a pipeline. Now, by 2021, we are basically at a point where most of the most impactful machine learning models at Uber are using deep learning. And they are increasing demand bigger and larger models, training with lots of more data, and being more performant. Our stitched together architecture is pretty complex and increasingly become fragile. So this is when we turn to Ray. What we found is that Ray provides very powerful and simple primitives for distributed computing, such as remote tasks, and it supports hardware aware of this task scheduling. So that let us be able to carefully decide what needs to be executed on CPU and what needs to be executed on GPU. So here's where we are. We have, right now, we are on a journey to replace the majority of the components of deep learning, of machine learning pipeline with Spark. We are the first step, which we replace the training module, with Ray. We are the first step. We are expanding this Ray coverage from model training to next step is to transform and then to feature generation. Now, so this is our roadmap. With that, I'm going to hand over to Dee, who is going to talk about the large-scale deep learning training with Ray.
All right. Hello, everyone. My name is Dee. I work at Uber in the Michelangelo AI team. I'm glad to have this opportunity to talk to you about how we actually integrate Ray into our training pipeline. So basically, this is a very high-level view of how our training pipeline looks like. We have a bunch of feature preparation, transformation stage to get the data ready. Those are based on Spark executors. And then when it comes to the model training, we bring up a backend based on Ray, which can efficiently and very conveniently train the models. And then for later stage, we go back to the Spark executor. So my talk will be focused on the red part of the diagram, basically how we use Ray open source to enable offline trainer running in scale. We actually had already evolved 2 generations of Ray. This is our first generation. Basically, I want to show how we actually bring up the Ray cluster. On the left side, you can see the trainer main process actually will reach a point where it calls a Ray up command, which the command will be sent to the job gateway, Michelangelo job gateway. The Michelangelo job gateway will actually parse a request and then send the call to a scheduler. We have our backend running on-premises data center, which is using Peloton as a scheduler, or we can run on Google Cloud, which uses Kubernetes. So this scheduler will actually provision the Ray cluster basically in a manner that it brings up the header node and the worker node of the Ray all together. And then the header node and worker node will use a timeout strategy to synchronize and get render votes. Once the Ray cluster is ready, it go back. The train main process on the left side wait for the return of this call. And then once it gets the return, it knows the Ray class is ready. It will create the Ray client link to the cluster and start running jobs on this Ray cluster. So once the Ray cluster is provisioned, the overall architecture is relatively simple. We have header node, worker node. I just draw one worker node here. The header node, worker node are identical in terms of hardware specification. They both have a GPU on them. We run the training process on the GPU, and they both have large memory CPU. We run the data loading and shuffling process on them. So basically, this kind of force the one-to-one match of data loading or versus the training processes. The header node itself also need to take care of the master management. So this is an architecture of a first generation. We call it a rigid Ray. For rigid Ray, I want to compare the pros and cons of the setup. Basically, it's very straightforward to implement. It's getting us started with working architecture. Basically, at the moment, the majority of our deep learning workflow running on such configuration. But very quickly, we discovered the limitation of this configuration. Basically, the I/O and compute process has to be 1-to-1 ratio. The cluster size, once provisioned, is kind of fixed. It lacks the elasticity and the fault tolerance, which actually come with the Ray open source. So we very quickly evolved into our second generation heterogeneous Ray cluster. The provisioning step slightly different here. The kicks on are still the same. The train main process sends marry up command to our job gateway. The job gateway sends the provisioning request to our scheduler. The difference are when the scheduler actually bring up the instance, for the new generation, we actually just bring up the head node. And then we leverage the autoscaler capability provided by Ray open source to directly bring up the rest of the cluster. So basically, we just need to provide a configuration file to the head, and the head node will automatically bring up the rest of the Ray cluster. And then the synchronization and wait for the Ray cluster to come up will pretty much still be the same. So once the cluster is up and running, we can have, for example, a configuration like this. Basically, we have a dedicated head node. This time, the head node doesn't have GPU process on them. The head node doesn't run the training or data loading anymore. It only manages the cluster. It takes care of the auto scaling and also collecting Prometheus metrics, collecting the logs. The trainer node can be specified with arbitrary number of nodes, arbitrary number of GPUs on each node. I draw an example of 2 GPU worker here. Basically, the trainer node will be dedicated for training. It doesn't have to do the data processing, the shuffling anymore. We decouple the data shuffling and data reading to the data nodes, which is in the middle column, 3 of them. I draw 3 of them, which are pretty much a very compute intense, memory intense. It needs, we use the Ray data provided as a module in the Ray open source software to run these data trainers. So the benefit of having the heterogeneous Ray cluster is we're able to kind of isolate the I/O part and the compute part of the model to different cluster. And then that allows us to flexibly configure different I/O to compute ratio to match the characteristic of each model. Because each model can be different. Some models are more complicated, need more compute, but some models need to read more data, which needs more I/O. And then we leverage the object store provided by Ray so that we can do like semi-global shuffle. Basically, the data shuffling will be carried out in a much larger scale. And also by isolating the data reading process and the training process, we are much easier to, say, diagnose what's happening inside the Ray. If something went out of memory, we will be able to know exactly which process caused it. So this decoupling helps us with debugging and monitoring the Ray cluster as well. And also, we can leverage the native elasticity of Ray, which is a very powerful feature as well. So I want to give a concrete example of how the performance actually gets better when we switch to heterogeneous cluster. This is used a training of a I/O intense model. Basically, you can see even if the node number looks more, each node we can have less resource assigned to them. So the overall, which is the 4th line total CPU core memory used, are reduced with heterogeneous Ray cluster. However, we were able to actually improve the performance because now we decouple train and data reading. Each of the CPU or GPU can be carried out at their peak capacity. So we have savings on GPU, CPU memories, but also we have a throughput improvement. So after this, I'm going to hand my talk to Michael.
Sorry, let me quickly test this. OK. Oh, sorry. OK. Hey, everyone. So my name is Michael. And today I want to kind of just share a little bit about kind of our journey of evolving hyperparameter optimization at Uber. starting with how we built our first hyperparameter search service to kind of tune our models. Some of the challenges we actually observe along the way as we try to tune larger and larger models, and how bringing in Ray actually help us tackle some of these challenges. So to start, let's just do a quick recap, right? So hyperparameter search, as many of you know, is the process of choosing a set of optimal values that maximizes your model's performance, right? But unfortunately, our resources are finite, so we cannot just naively kind of try out every single combination of them. So we started with the standard grid search and random search, but very quickly we moved towards more Bayesian-based approaches as search space starts to become more complex, and evaluating each hyperparameter combination, which we often call it a trial within a study, becomes more and more expensive. So essentially we have to train and evaluate a model for every trial, which means that as we continue to scale our model, this process is only going to be more and more costly, both in terms of time and compute. Fast forward to 2018, we built AutoTune as our first black box optimization service to kind of scalably guide all the tuning process at Uber more intelligently. And on a high level, our first AutoTune workflow kind of looks a bit like this, right? So I want to tune a job, so I will go to Michelangelo, kick off a hyperparameter search job, which will then create a study. AutoTune will then return a bunch of trial suggestions, which are essentially just hyperparameter values for us to try. Michelangelo will then take those values to train the model, evaluate it, and send the results back to AutoTune to basically let it know whether the previous suggestion was a good recommendation or not, right? And based on that, AutoTune will send more suggestions, and then we'll keep repeating this process until we find the best candidate. But the underlying control plane of the system is quite similar, but there's actually a few differences or important details that I would like to call out, right? So first, after Michelangelo kind of creates a study, the request actually gets rerouted to our workflow service, which will then materialize a static, logical, and physical plan of how the trials should be scheduled and executed. Different trials will then be scheduled and launched on different distributed clusters. And depending on our logical plan, we might fuse one or two trials within a single to be executed on the same cluster. Another thing we want to call out is that to ensure resource isolation and loose coupling between the AutoTune service and the library, the AutoTune workers actually will launch Docker containers on different resource pools in order to generate suggestions. So that was the first version of our AutoTune service, right? And that was actually enough to get us to our first tens of millions of trials. But we quickly hit some bottlenecks. So in the next version, we added a few improvements. First, we added dynamic control flow and just-in-time compilation to our static ML workflows. This allows us to dynamically change the study execution based on runtime data evaluation. This is super helpful, actually, for us to, say, introduce some kind of custom retry logic for a specific failed trial, or some early stopping mechanism to globally stop a study if it's no longer improving. And combined with some simple meta-learning strategies on historical studies to kind of extrapolate and warm start future studies, we're actually able to dramatically improve the runtime efficiency of all our studies by about 50%. Another thing we actually wanted to improve was actually the latency of the end-to-end latency of generating kind of each trial suggestion. So basically, we gradually move away from scheduling and polling AutoTune Dockers towards more inline parallel execution. This actually dramatically reduced the number of dangling studies that we have at each single time, and it's super actually useful for users who want to, say, just spin up 100 trials locally on their machine. And just try out their workflow quickly before pushing that to the remote cluster. But again, as we start to tune larger and more complex models, especially for deep learning models, new challenges arise, right? So first, as each trial takes longer to train, we realize we actually need an even more aggressive early stopping than before, right? So instead of actually waiting for each trial to actually complete before we make more trial suggestions, there are actually successive halving techniques that can monitor the progress of every ongoing parallel trials after every X iterations, and then prune the candidates that actually are less promising. And this actually gives us a way to, say, guarantee to finish a study within a fixed budget. And next, I think for dynamic schedules, we realized that for deep learning models specifically, it's super important for us to actually change the hyperparameter values throughout the training process in order for us to get the state-of-the-art performance. What this means for the hyperparameter search process now is that we actually have to find a schedule of how each of the hyperparameter values need to change after every iteration, instead of just finding a fixed set of optimal values that can be used throughout the entire training process. And finally, we also want to make sure that we can elastically scale our workers in an auto-scaling environments to maximize our training throughputs, convergence, and minimize costs, right? So for example, this could be if we want to gradually increase the batch size over time, how many workers can we actually allow to freely kind of enter and exit the cluster without actually impacting the training throughput? And then obviously, we also need some kind of like compute framework that allows for that flexibility. So for our next version of our AutoTune, I think one core piece that we actually have to incorporate is some kind of like central orchestrator that has full visibility and granular control over how each of the trial needs to actually happen, right? And while actually maintaining very, very minimal overhead. This is super important because we want to make sure that each trial suggestion still happens super quickly so that users can actually quickly try their workflow locally and push it to the remote cluster without much friction. And another thing is that we want to make sure that we decouple kind of the interface and the logic and the abstractions between trial generation and suggestion so that we can quickly try out new techniques like ASHA and population-based training. And as it turns out, these are actually essentially problems that RayTune can help us address. But before we can actually incorporate RayTune, we actually have to first move the common distributed trainers at Uber, like XGBoost or DL frameworks on Horovod, onto Ray as a unified compute layer. And we introduced elasticity to XGBoost and Horovod on Ray to allow distributed training to kind of scale the number of workers throughout the training process. And as part of this initial work, we kind of solve the problem of fusing the compute environment between Spark and Ray. And for DL specifically, we also have to build integration between Horovod and RayTune so that you can start trials using Ray actors, with each Ray actor actually spinning up elastic Horovod workers. So we shifted the AutoTune's kind of internal state machine logic more towards into Ray, and updated our workflow compilation logic to generate a unified workflow for our training and tuning workflow. We can now basically essentially run an entire study within a single Ray cluster, which will help us avoid the need to kind of like maintain multiple Spark clusters for parallelism, avoid the scheduling, and as well as the data loading and shuffling costs into each distributed workers for each trial. And we also connected RayTune to our checkpoint manager to have efficient trial recovery. And we actually expanded our cross-study services within our AutoTune service to better warm start every single RayTune session. So RayTune can now actually can efficiently manage the end-to-end. Oh, sorry, I actually didn't click. RayTune can actually manage the end-to-end kind of execution of every single study. But across different studies, our warm start services, our cross-study services will actually kind of manage intelligence across studies. And this is super important as we start to kind of pair our retuning strategies with stuff like incremental training and transfer learning as we continue to scale deep learning. So now let's take a look at some results, right? So compared to our previous AutoTune as a baseline, the first row actually highlights the efficiency improvements simply from adopting some more aggressive early stopping strategies like ASHA. So this is roughly measured by the total number of iterations and trials that we can prune from the algorithm. And from this, we already see a 4x speed up on top of our previous early stopping strategies. And on top of that, on the second row, just by running everything on a single array cluster and saving the cost of managing multiple Spark cluster, data shuffling and loading, we see another 2x speed up on top of just using more aggressive early stopping. And we're able to actually achieve all these results without actually compromising the performance of the models, right? Which is actually kind of important for a tuning job. The model improvement with Asha is actually a bit lower, which is fully understandable because we're actually applying a very, very aggressive early stopping. So essentially what we're doing here is trading off full explorations versus some kind of like tuning efficiency. And other than performance, because of how Ray Tune can actually decouple and then expose the different logic of trial generation and suggestion, we actually now can inject custom acquisition functions to, say, talk to our feature store or our model libraries to kind of expand and parameterize kind of the search space beyond just hyperparameters into architectures, techniques, and feature transformations. I'm also very excited by Ray's new AI runtime, which also included a new tunable dataset concept, which is very, very relevant for this joint exploration work. And finally, just to wrap up, a couple of things that we're also actively exploring and would like to share some results soon is how to do parallel exploits with dynamic resource allocation, which means that we can potentially go even faster by just diverting and redirecting resources to more promising candidates along the way. We also want to continue to improve our cross-study services to better use stuff like learning curve extrapolations to extrapolate from the 100 millions of trials that we have done already to better guide our future tuning studies. And finally, we want to kind of extend, just abstract out all the good stuff from RayTune to generically support other complex training patterns at Uber, like model partitioning or model ensembling. Thank you, and I'll hand it back to Shu for closing remarks.
So I'll be real quick here. So number one is that as you can see, over the past 6 years, we went through 3 generations. This is because the ML platform technology evolved really, really rapidly. And then with the technology evolve, our business use case also they are increasing demanding. In our experience, we really find that Ray provides the best sweet spot in terms of giving us the flexibility and also the strong ML ecosystem for us to move forward. And finally, I think this is the most important point, is that the Ray team is really, really awesome. We have great collaboration with the Ray team, and especially Richard, Chen, Chris, Kai, Jen, and Zhe. I think without these folks working with us along the way, we will encounter much more challenge. Before we part, I also want to point out these are the blog posts and conference appearances we had in the past about Michelangelo, and these go way deeper than the 30-minute talk we have here. So please check it out and do a deep dive. I'm happy to chat offline with all of you. Thank you.